it's been great to hear about Koji's exciting research for the last couple of years. He's a professor at Osaka University and has a number of very cool results in this direction, and he's going to tell you all about it today. So without further ado, thank you very much, Koji, and take it away.
Thank you very much. Thank you for the introduction, Jim, and also the invitation to this wonderful seminar series. I'm Koji Hashimoto from Osaka. Hello. I'm in Japan, and in Japan, it's midnight. It's 1 a.m. So I woke up 1 hour ago. And then, yeah, I hope my neural network in my brain works properly. And I hope I can entertain you in this 1 hour. So thank you very much for joining my talk. So this talk is based on my collaborators. Here I list my collaborators. Hong-Yen Fu, Izan Yo in UCSD. And in particular, Izan Yo actually developed a very similar idea of relating quantum gravity to deep learning. So please check his papers out. And also with my students, Akutaga and Sumimoto, and also postdocs, Sugishita, Tanaka, and Tomir. They're working in string theory also like me, or lattice QCD, or machine learning. So we get, various fields, researchers get together, and this talk is based on that. So let me start with my personal history. So in fact, I started this kind of research connecting deep learning and quantum gravity 3 years ago. I noticed 3 years ago, as Jim said, there was a rise of very rapid development of machine learning. And so I organized one workshop or symposium in Japan. The title was Deep Learning and Physics. And until this symposium, I have known nothing about machine learning. But in the talk, so there are various interesting machine learning talks, including from Professor Amari. And I noticed a similarity between my field and machine learning. So on your right, this is a famous deep autoencoder neural network. And on the left-hand side, I draw a figure from my paper in quantum gravity. So quantum gravity is a subject in which actually you want to relate quantum and gravity. So they are independently developed. I'll show you some history of quantum gravity. And now it's really time to find the complete formulation of quantum gravity. We are in that era. And I'm string theorist. I'm working on quantum gravity only. But I want to actually import some very vast and nice knowledge of machine learning to our field, quantum gravity. So on your left, here it's a figure of wormholes in Penrose diagram of so-called maximally extended eternal area Schwarzschild black hole. So to some of you, this word doesn't make sense. But this is a very important picture and figure for me. It represents a wormhole in black hole geometry. And we want to know what's inside of the black hole. Once quantum gravity is complete, then we have a description of the inside of the black hole. Okay. And then if you want to probe inside of the black hole, then you need to probe, put some probe or something into the black hole. And in fact, there is a conjecture that inside of the black hole is counted by some kind of network. So this figure, to me, looks really similar to this neural network. And I was very shocked. Since I have never imagined that this activity of machine learning can be directly related to quantum gravity. But here, from this similarity to me, I found that there should be a very close connection between these two. And in my talk, I'd like to actually make a bridge, a concrete bridge between quantum gravity concept in these days and neural network. So I hope you enjoyed. So here I prepared a roadmap of my talk today. And if you look at this whole picture, then I hope you can understand my roadmap. So on one hand, I prepare a quantum gravity system. So this cartoon is something which represents general space-time, which is wiggled and curved. And gravity actually is the system which treats curved geometry. So in general, we prepare some curved space-times and then try to describe how time evolves or which kind of space-time is chosen from Einstein action. So that's gravity. And quantum gravity means that you treat quantum mechanical effect of gravity. So this cartoon actually represents, for say, two-dimensional space, curved space. On the other hand, I prepare a quantum mechanics in one-dimensional lower space. So if this is 2 dimensions, then this is 1 dimension. So these arrows indicate spins. So in quantum mechanics, as you know, it's a microscopic description of this entire world. So if you look at spin atoms, then on each atom you have spin up or down. And then the collection of the whole thing will give you the material. For example, the magnetization is made of each spin. So this is a one-dimensional alignment of atoms. And then on each atom, for example, there are spins like this. And this is one-dimensional quantum mechanical system, which has no gravitation, okay? So this is just quantum mechanics, which we learn in undergraduates. And in fact, there is a nice conjecture which relates these two things. On the one hand, you have a quantum gravity system in d+1 dimensions. So it's gravitating system, so it's about curved spacetime. There is Einstein equation, and that describes the curved spacetimes. On the other hand, you have lower dimensional quantum mechanics, which is non-gravitating. And these people, Hooft and Susskind, conjectured a so-called holographic principle. And Maldacena in 1997, he discovered a concrete example of this equality working. And this is called ADS-CFT correspondence. And I'll explain that more in detail later. And this conjecture, if it's true, would be very, very important since quantum gravity is far from completion for now for human beings. We want to find the description of quantum gravity. Quantum system developed for 1 century, gravity system developed for 1 century for research, but they never merged. And if we can merge these two things, then that's a final goal of fundamental physics, one of the goals. So to relate these things and to prove this conjecture is one of the fundamental goals of quantum gravity community, which is like 2,000 people in the world. We are working on that. And in this talk, I'd like to relate these two by using machine learning. So how do I do it? So in fact, there is a nice description of this quantum mechanical system of 1 dimension. So if you look at these spins, then if you flip one spin like this one, then it will affect the next spin. So if you flip this one, then this could just flip with some probability. And this is called entanglement, quantum entanglement. Okay, so this is preferred, or this is preferred, or this is preferred. And how these atoms are quantum entangled is now nicely represented by this kind of network. For example, this square is called this entangler. That means that this one and this one is nicely entangled together. And once you are given a system of quantum mechanics, like Hamiltonian, if you're given, then you want to solve what is the ground state wave function. And this wave function actually encodes the information of the entanglement of each spins. So if you draw this kind of figure and assign some numbers for these square and triangles, then this actually represents the ground state wave function. So that's the idea of tensor network. It has been developed for many years. And it worked very nicely to make an ansatz for the ground state wave functions of quantum mechanics for given Hamiltonian. And in 2010, Swingle made a nice idea about this interpretation of tensor network. If you look at this quantum gravity, quantum mechanics correspondence, then this tensor network looks like the one-dimensional atom is extended into another space. And he identified this tensor network part as a space-time with one higher dimension. So this is called anti-de Sitter space-time. Anti-de Sitter space-time is a special kind of homogeneous space with negative constant curvature. So why this space is interpreted as this tensor network? The answer is quite easy. So if you try to divide this anti-de Sitter space-time with the unit volume, then it looks like this. So since this space is negatively curved, and this is called ADS boundary, anti-de Sitter space-time boundary, and suppose you divide this boundary into 4 parts. Then if you go deep inside, then the unit volume changes like this and like this. So 4 becomes 2 and 2 becomes 1. So it's exponentially shrinking, okay? And if you count the number of these boxes, then if you put a square for each unit, then actually this picture is the same as this picture. In this way, the structure of anti-de Sitter space-time looks really similar to this tensor network. And this tensor network, in particular, the tensor network with the name MERA. MERA is an abbreviation of multi-scale entanglement renormalization ansatz. If you do that, then that tensor network actually has this structure. So 2 combined into 1, 2 combined into 1. So Swingle pointed out the similarity between this anti-de Sitter space-time and the tensor network. This is quite nice, since on the one hand, you have just the quantum mechanics, but the information of this ground state is extended into another space. And then this is interpreted as anti-de Sitter space-time, which works very well in this correspondence between quantum gravity and quantum mechanics. But reality is that I want to extend this anti-de Sitter space-time, which is almost flat, constant curvature, nothing there, to a general space-time, which is wiggled and general curved space-times. So if this generalization is possible, then I think we have a better understanding of quantum gravity. So to do that, I'm gonna use this generalization of tensor network to neural network. In a seminal work by Kari and Troyer, they used a neural network representation of quantum mechanical wave function to find the ground state. And this worked very well, as I will review later. And the neural network is a candidate for having a quantum mechanical ground state wave function. And now, suppose that in a similar way as Swingle did, we can map this neural network to a general space-time. Of course, it's questionable, but if it is possible, then we have a Farmer bridge between quantum gravity and quantum mechanical system. There is a difference of dimensions, but this difference is supplemented by the extension of the depth direction of the neural network. But this question mark is a big question mark. If I can work out when neural network is interpreted as a space-time, then I think it's having a big effect on the research of this equivalence between these two interesting systems. So this is the roadmap, and I divided my talk into 4 parts. The first, I will give a review of quantum gravity and quantum mechanical systems, why they are equivalent. And then in section 2, I will give another review of how people generalized tensor network to neural network states and how good it is. And then in section 3, I'd like to ask when a neural network is interpreted as a space-time. So there are many severe conditions for that to be possible. And then in section 4, I'd like to combine all of these ideas to show you an explicit example of emergent space-time out of neural network by feeding in some quantum mechanical data. Okay, so this is the section list. In section 1, quantum gravity. Section 2, I'll review neural network quantum states. And section 3, I'd like to ask a question: when is neural network as space-time? And then in section 4, I'll show you space-time emergent from data. And if time allows, I'll give you some discussions. Okay, so let me start with section 1. This is just 3-page review of what quantum gravity is to non-expert. So here is a brief history of quantum gravity from my viewpoint. So what's the difficulty in quantum gravity? In 1974, Tofuta and Veltman found that perturbation theory fails in quantum Einstein gravity. So we all believe that gravity is based on Einstein equation. And on the other hand, the elementary particle physics is based on so-called quantum field theory. And in quantum field theory, because the perturbation works very well, it is mathematically consistent. It's believed to be. On the other hand, if you naively use the same perturbation technique to Einstein gravity, then there appears divergences and it is uncontrollable. That is what Tofuta and Veltman found in 1974. On the other hand, there was a development of string theory. In 1970, Nambu, Susskind, and Nielsen found that hadrons may be described by string theory. And then in 1974, Ionea, Shirk, and Schwartz found that strings actually includes gravitons. So string was reborn as a quantum gravity. The other sequence of the history is that in 1971, of course, gravity hosts a black hole as a typical object. And people looked at the entropy, so how many states are included in gravity. And then Bekenstein proposed one formula of black hole entropy. This entropy formula was very interesting. Entropy is proportional to the area of the surface of the black hole, that is event horizon. So normally entropy is proportional to volume, but in the gravitation system, he found that entropy is proportional to area. So one dimension lower. And based on this argument, in 1993, Tofuta and Susskind proposed a so-called holographic principle. So they basically said that quantum gravity system in, say, 3 dimensions is dictated by 1 dimensional lower quantum mechanical system, which is non-gravitating. So this is called holographic principle. It's like a hologram. So universe as a hologram of a 2-dimensional quantum mechanical system. And later in 1997, Madasina found this ADS-CFT correspondence. This is based on string theory, and string theory actually occurs perturbation theory of Einstein gravity. And this ADS-CFT correspondence born out of string theory is a concrete example of this holographic principle. So Maldacena gave a pair of quantum gravity and quantum mechanics, both given by some Lagrangians, and he said that the did would be equal to each other. So this is the birth of so-called holographic principle and the ADS-CFT correspondence. So let me tell you more about this ADS-CFT correspondence. One slide in words and one slide in equations. So what is ADS-CFT correspondence? Based on this, I'm giving my later part of the talk. So please allow me to explain this kind of difficulty looking concept. What is ADS-CFT correspondence? So CFT, this is an abbreviation of conformal field theory, but you don't need to understand what CFT is. It's just the quantum mechanics in, say, d-dimensional space-time. Then what is ADS? ADS is the abbreviation of anti-de space, or space-time. It's a quantum gravity and d+1 dimensional space-time. And these are equal to each other. Of course, on the left-hand side, there is no gravitational force. On the right-hand side, there is a gravitational force. So they appear to be very different from the first place. So they are dictated by different Lagrangians or different Hamiltonians. And Maldacena conjectured that these two are physically equivalent to each other. So there are 4 comments from me. First of all, there is no proof about this equality. So even though you say that this is equivalent, of course you have to show it. So what people did is that, so people computed some quantity, physical quantity out of this quantum mechanics, and some other quantity out of this quantum gravity computation, and they showed that they have the same value. So with this kind of computations, there are a vast amount of evidence known, but there is no proof. Mathematically and or even physically, there is no proof. So a particular question is that suppose you are given left-hand side. So suppose I have my favorite quantum mechanical system like Heisenberg model or something. Then can we find the right-hand side? I mean, its gravitational equivalent. So this kind of question is too difficult to be answered right now. And maybe because of that, Madasena's paper is top site. So if you look at the high energy theory papers, there is a website called Inspire, which collects all the high energy theory papers. And Madasena's paper is cited most. And the number is far beyond the Nobel Prize papers. So you can understand how this is important in our community. So the quantum gravity is too difficult. So there is another version of this ADS-CFT correspondence, that is this. So you replace this classic quantum by classical, then classical gravity is much easier to treat. So is there equality for the case of classical gravity? The answer is yes. So you need to take a large degrees of freedom limit. So suppose, so in a previous figure, I have just four atoms. But 4 is replaced by n and n to infinity, then you have a large degrees of freedom system. And it is believed that this large n limit corresponds to classical gravity. So we can work in this easier scheme as a first step to understand quantum gravity. So this is explained by words, but I'm gonna tell you with the equations. So when you equate 2 systems, this is a bit difficult, technical part, but please allow me to explain. When and how can you show the equivalence of 2 systems? Of course, when Lagrangian is the same, then it's the same. But suppose Lagrangians are different, then how can you show the equivalence? The answer is to compute a so-called partition function. So partition function is made out of Lagrangian, and it's a number, and it can encode every tiny bit of this Lagrangians. So it encodes all the information of the system. So once you say that the partition functions are the same, then it shows the equivalence of this physical system. If this is just numbers, then there is no further meaning of that. But if this is functions, then functional equivalence is much non-trivial. And so you can say that these 2 systems are the same. So what is the partition function of quantum mechanics? So once you are given a Lagrangian, and Q is the dynamical variable of this quantum mechanics, then you make a path integration of this Q of T with the exponentiation of this action of the quantum mechanics, then that defines partition function. If that's it, then it's number, but I want to make it a function. So a function of what? So you introduce a so-called source function. This is explicit function of your favorite form. And then you couple it to some operator q. This O of q could be just q or q squared or q to the triple, whatever you like. So you pick up one operator and couple that to the source. And then you make a path integration. Then you get a partition function, which is a functional of this source function phi 0. So phi 0 could be, for example, in the case of quantum mechanics, it's a time-dependent explicit function. So in this way, this partition function is defined. So what is the counterpart in classical gravity? So classical gravity, of course, has a partition function too, but it is based on different Lagrangian, which is almost like a generalization of Einstein-Lagrangian, Einstein-Hilbert action. So it's written like this. This is the Einstein or gravity action and exponentiated. Since this is a classical system, not quantum, so you don't need to make a path integration, but you have to substitute a solution of equation of motion of this metric function g and scalar field phi back into this action, then evaluate this exponentiation. That's the definition of partition function. And what is phi 0 here? Originally, it was on the left-hand side, it's a source function. And on the right-hand side, this source function is identified as a boundary condition here. Since this is in a higher dimension, there is another space direction, z, and phi 0 works as a boundary condition for this scalar phi at the boundary of this space-time, and also the boundary condition for this metric function g. Okay, so you solve the equation of motion of this higher dimensional space-time by starting with this Lagrangians, and then you get classical solution phi and g with this boundary condition, and then you substitute this back to this action. Then this action is a functional of phi 0 of t, so it defines a classical gravity partition function. And ADS-CFT correspondence states that there are two independently looking systems, but if you compute partition functions of both in this way, then you have an equality for the partition function. So the difficulty here is that even though you are given this left-hand side, there is no way to guess what is the right-hand side if you don't know what the Lagrangian is. So for example, suppose this part is missing. Suppose I didn't know the Einstein-Hilbert action. So it's written by the metric function of this curved spacetime, but I don't know the action. So I don't know what the classical solution is. But if ADS-CFT is true, then from a given quantum mechanical system like this, you may have a counterpart in gravity system. So I want to find out what is this classical solution for the metric, for example, that defines the higher dimensional spacetime. Good. So this is the end of section 1. So I finished section 1 here, the review of these two. So you may vaguely understand why this is important in our community, and also how this works so if you want to go from here to here, then you need to look at the partition functions. All right, so let me go to section 2, the review of neural network quantum states about this part. So this is a completely different looking subject. So it's in condensed matter physics with atoms. So in the condensed matter physics, there is a very big development for the last 3 years using neural networks. So I'm gonna explain that. So what is the most important issue in condensed matter physics? The most important question is to find the ground state wave function. Suppose you are given a Hamiltonian of quantum system, so spins are aligned and how they interact, that defines the Hamiltonian. Then for a given Hamiltonian, you want to find a ground state wave function by solving, say, Schrödinger equation. But solving Schrödinger equation is very difficult. So the other way of doing this is to put an ansatz for this ground state wave function and then minimize its energy, which is expectation value of this Hamiltonian H with this ground state wave function. So E is like a loss function in machine learning. So you want to make it decrease by changing the parameters of this ansatz of the ground state wave function. So notice that this ground state wave function is dependent on each spin of each atom. So suppose you have vast number of atoms, like Avogadro number, then this ground state wave function has an enormous number of parameters. So condensed matter people tried many nice ansatz. So one of them is so-called matrix product state, which actually relates each atom adjacent to each other by these so-called tensors. So this is tensor network. And if you assume that this tensor has the same value as this tensor by putting some translation invariance to the system, then you can incredibly reduce the number of parameters. And this helps us a lot to find out ground state wave functions. And also tensor network states. This works for critical points and critical phenomena, ground state. And you introduce A and B like this. And then this defines the tensor network states. And you vary the numbers or values of these A and B tensors to reduce this value of the energy. And when it reaches the bottom, then you say that this is a candidate for the ground state wave function. So now I think if you're from machine learning, then it's almost obvious to you that you can use a neural network. Since in neural network, in Boltzmann machine or feed-forward, you have a so-called universal approximation theorem. So if you increase the number of units in hidden layer, then you have more representative power of this functional form of neural network. So Cario and Troya in 2016 as a preprint, they used a restricted Boltzmann machine as a ansatz for representing the ground state wave function like this. So they introduced hidden layer and visible layer. And this visible layer is the argument of the ground state wave function. And they tune these weights such that the energy decreases. So it's not about loss function and classification network. It's about the output of this neural network. And so in this case, it's a probability distribution. And use that as an ansatz for wave function and evaluate the energy as an expectation value of Hamiltonian, then try to reduce that number. And it has been generalized to deep Boltzmann states, like introducing more layers. And also feed-forward neural network states has been used. So in this case, you have alignment of spins here, and output is here, and use this output function as an ansatz for the ground state wave function. So these are typical neural network states proposed, but nowadays, in particular, young people in condensed matter physics use a lot of this technique because this was really successful in the work of Cario and Troya. So I'll show you one of their results. So they used a particular Hamiltonian of the system called two-dimensional anti-ferromagnetic Heisenberg model. This is a kind of key model to test ground state wave function. And here is a figure of how neural network states worked. So the horizontal axis is number of hidden units. So you can increase number of hidden units. And the vertical axis is the energy with this restricted Boltzmann machine ansatz. And then you can see that the total energy goes down once you increase the number of hidden units. And it exceeds and goes below these two dashed lines. They are using the conventional tensor network like wave function ansatz. So they can go even below them. And this is a huge success. And people argued why this works. An idea of understanding why it works is as follows. So there are many intimate relations between neural network states and tensor network states. So people discovered intimate relation. For example, one tensor network state is given, then you can construct a neural network representation of that, and vice versa. And because of this, maybe this neural network states includes the previous tensor network states, but it expands the category of ansatz functions to a nice way, in a nice way. And recently, for example, the paper last year, so-called matrix product operator network was proposed in machine learning. So it is kind of inverse import of the idea of condensed matter physics to machine learning. And people argue that this MPO net works very well in machine learning. So this is the end of my story in section 2. So I described how people replace this tensor network by a neural network in a better way of their question, answering their questions. So I may go on to section 3. When is neural network a space-time? So it is about this part. So suppose you have a neural network, then when this neural network is interpreted as a space-time. If that kind of translation from neural network to space-time is possible, then I'm going to use it to interpret this neural network by general space-time to probe the equality between these two. So let me ask this question: when is neural network a space-time? I have 5 slides for this. So obviously, there is a general neural network is not a space. So look at these very typical old neural networks, perceptron model, Boltzmann machines. They don't look like a space. So if you want to understand this as this direction as space or time, then how can we do that? Since in this all-to-all connection neural networks, there is no notion of which unit is close to which. So there is no notion of locality. And in physics, locality is very important. Of course, physical law is translation invariant. So if physical law is correct here, then physical law is correct there. And also we impose the locality condition. That means that if something is happening very far away from you, then it will not affect you, right? So locality is one of the most important concepts in theoretical experimental physics. A neural network doesn't have that. But if you add sparsity and also weight sharing for the neural network, then neural network can have locality. So this is fully connected neural network, which has no locality, but once you impose locality, like in the convolutional layer, then you can say that this unit is close to this one and this one and this one, but not the others. So locality is imposed by using this sparsity and sparsity. And also you can parallelly translate this line to this line and this line to this line. And suppose you do a weight sharing. And this means that the physical law around here is the same as the physical law around here, right? And we need to use this to interpret neural network as a space-time. And you know that physical laws are all based on differential equations. So what is differential equations? Differential equations is made of the field phi and also the derivative. The derivative means that if you consider a translation from one point to the other, which is next to you, then you look at the difference. And if they are far from them, if they are far from each other, then you need to act derivative more and more, and you have many, many derivatives. And you all discard all of those higher derivatives and consider only 1 or 2 derivatives. That's a physical law. So restricting ourselves to those local things, or rather to say some homogeneous low frequency modes, then you have to go to this locality imposed neural network to interpret neural network as a space-time. So this story is about this vertical direction, but what about the horizontal direction? In fact, the neural network depth can be understood as a time, a kind of time, once sparsity is imposed there. So dynamical system like this, so suppose x is the location of the particle at time t, then time evolution of this x is given by this velocity is given by some force, x-dependent force. And if you discretize time direction like Tn plus 1 equal to Tn plus delta t, then this differential equation is replaced by this equation. There, you see that the derivative, time derivative here is replaced by x and x difference. And you all know that the residual network has the same structure. ResNet is an easily trained deep model, so people use this a lot. And the neural network looks like this. So there is a weight linear transformation plus activation function f. Then this is the normal feed-forward neural network. But in addition to that, you introduce so-called skip connection that directly put this value into this as an addition. And this skip connection is the same as this one. So this means that the residual neural network is a reminiscent of this dynamical system, and time evolution is given by the neural network feed-forward. So as a summary, if you put sparsity and restrict your neural network architecture, then there is a situation at which this neural network is interpreted as a spacetime. So for example, suppose you are interested in Hamiltonian dynamics, and then suppose you don't know the Hamiltonian, but you know what's the time evolution of the data. Then can you find this Hamiltonian? The answer is yes, if you use this technique of sparsity and weight sharing in the neural network. So how it goes is like this. So this is the Hamilton equation. H is the Hamilton, I'm sorry. H is the Hamiltonian, and Q and P are dynamical variables. So suppose I have just two dynamical variables. Then if you can represent this Hamilton equation in terms of neural network, which is sparse and weight shared, then you can use this neural network as a simulation of time evolution, and you put the data of this point particle as time evolves, it moves to this point. Then use this data to find the Hamiltonian as a weight and also activation function. So I don't go into the detail of this neural network structure, but there is a way to represent this Hamilton equation in terms of Q and P neural network. And here, W is the linear transformation, Y is the activation, and W is another linear transformation. And you combine these two with very sparse weights, then you can reproduce Hamilton equation with this quite generically looking Hamiltonian. So here, the arbitrary function G and F is nothing but the activation function itself. So if you can tune the coefficient of activation functions, then you can explore various kinds of Hamiltonians. And from the data, you can find this Hamiltonian. And also, this step is just one time step. So the Hamiltonian can change in time, right? So if you have the big data of the position of this particle and velocity, and then you can find this time-dependent Hamiltonian by using technique. So the final slide in this section 3 is, for example, can you find a Hamiltonian? So let me read this question for you. So consider a particle motion x of t in a given potential Vx in one dimension. So the potential is given, but with unknown time-dependent friction force, h of t. So friction force is normally proportional to the velocity of the particle. So h of t, this function is, suppose it's unknown. So to find out what is h of t, I tried many initial conditions at t equal to 0, and I collected the data at which this particle stops at t equal 10. Okay, I have a big data. Then the question is, from this given data set of initial conditions, which stops at t equal to 10, can you find h of t? The Newton's law is like this. So ma equals to the force, and you know this potential, but h of t is unknown. So what I can do is to represent this equation in terms of this neural network, and then seed in all of these data as an initial condition of feed forward and output. Then find these weights, and we interpret this weight as a friction force, the Hamiltonian. So in this way, we can solve the inverse problem of typical dynamical systems by using neural networks. And in fact, the reason why I explained this example is that, in fact, the quantum gravity question, which I'm going to explore in section 4, is indeed this question. It's equivalent to exactly to this equation. Okay, so this ends the section 3, in which I explained when neural network is interpreted as a space-time. So let me go on to the section 4, space-time emergent from data. So it's about this part. I'm going to use the knowledge of section 3 to bring in the gravity system and find the metric function of it from a given data of quantum mechanics. Okay, I think I have like 10 minutes. So let me explain this section 4. I have 4 slides. So what is the gravity side? So in the gravity side, I don't know what is the gravity action. So I discard it. And then I consider just, so the gravity side consists of 2 parts, the metric and some scalar field, which is called matter field. And I start just with this classical scalar field, but it is in a known higher dimensional space-time. Suppose the data is in 4-dimensional quantum mechanics, which is our world, then the corresponding gravity system is in 5 dimensions. Lagrangian looks like this, and this eta direction is the emergent spatial direction, the emergent other direction. And so eta is that direction. And in addition to the eta direction, quantum mechanical direction is these 4 directions. And here, metric G is given like this, and F and G, these are functions, which are called metric function of gravity, but F and G are unknown. And also this potential. So typically in particle physics, we take phi to the phi squared and also phi to the 4th. This is phi-4 field theory, which is very popular, but we don't know what the coefficient is. So these shaded parts are unknown functions. So we don't know what Lagrangian is. We want to fix this metric function by feeding some data. So what is the data? Data is the partition function. Partition function itself is a very difficult quantity, but if you work out the quantum mechanics, then you can give this data. And as I said, I translate this data into the boundary condition. So what is the boundary condition? This is higher dimensional space-time. And here at the boundary, you have the source phi-0. And this is going to be the boundary condition of the scalar field and its derivative. So this information is translated to these boundary conditions. But this space-time has another end around here. So what is this? In typical gravity system, what is the end of the space? End of the space is given by either it will be cut off smoothly or a black hole. So in my example, I placed a black hole here. Since in black hole, so as for black hole, if you go in the event horizon, then you can never come back. So this is the boundary of the space-time. And at the black hole, so suppose there is a black hole here, then this phi equation of motion should satisfy a particular boundary condition, which is this, equal to 0. So this is like you place this boundary condition at here, eta is infinity, and then you propagate it towards the end of the space-time. And then here is a black hole horizon. And if it satisfies a certain boundary condition there, then it's a good initial condition. If it doesn't satisfy this black hole boundary condition, then it's a bad initial condition. So in this way, you can discriminate. This one is a good combination or bad combination. And as you can see, this is a classification program. So these two are input numbers, and this is the output. So this is the label of whether this information is positive data or negative data. So in this way, you can rephrase the question of data to the classification program using this space-time as a neural network. So the second step is to rephrase the equation of motion coming out of this Lagrangian as a neural network. But that's easy. I'm gonna use the technique developed in section 3, the previous section. The equation of motion looks like this. So this is potential. And this h of eta is a metric function made of f and g. These are components of metric functions. So I combined f and g into this h, and this h is unknown. And as you can see, this equation is the same equation as the one in the question in section 3. Okay, so h of eta, in my case, in quantum gravity, this is the unknown metric function of higher dimension spacetime, but it was a friction force in the Hamiltonian of the system I described in section 3. So the question is, how can you find this one? And you know the answer. So first you discretize this equation of motion by regarding eta as a time direction. And then you introduce pi, that is derivative of phi, to make this second order differential equation to first order differential equations to make it representable by a neural network like this. In this evolution equation along eta direction, the horizontal direction, h is hidden here, and h is unknown, v is unknown. So these are hidden in these green lines. So green lines, these weights are unknown, but the black lines, their weights are fixed. So this is a very sparse neural network so that it has an interpretation that it is equivalent to the scalar field equation of motion. Okay, now we can train this model. In quantum mechanics, you have a lot of different quantum mechanical systems, but I use a QCD. QCD is a quark system, and it has been well studied, and it has a lot of big data. And quantum field theory has infinite number of big data, but I use a particular thing about QCD simulated by supercomputer. This is the plot of positive data plotted as blue and negative data plotted as orange. The horizontal axis is the source phi 0, and the vertical axis is the partition function. They have names. In fact, this is the quark mass, and this is the quark condensate. But never mind, this is the data from quantum mechanics. So I use this, then I train my neural network. On the right panel, you have the h function plotted, and this is the initial condition, which is zigzag. And I start machine learning to find out a consistent metric by this supervised learning. And the result looks like this. So when you run this code, then the machine tries to fit this given quantum mechanical data in a nice way. And the result is this emergent metric, which looks like a really smooth, nice function. And also you can train the values in the potential. Then using this potential, actually you can compute other physical quantities of QCD and compare it with lattice QCD simulation data. So for example, you can compute interquark potential from this emergent two-dimensional, so higher dimensional space-time by using string theory technique, and then compare that with lattice QCD data. Then they look quite similar to each other, surprisingly. So this means that this method of finding a metric out of quantum mechanical data worked very well. So this is the end of section 4. And I'm finishing and eating up my time. So I wanted to do some discussion, but just one slide. So I explained I explained quantum mechanical side and gravity side. Gravity side has metric and field. And I explained only the first part. So these are classical limit and large degrees of freedom limit. And in this case, I can use feed-forward neural network as I explained as an architecture. But truth is that we are going to quantum gravity. So how can we go to quantum gravity? In fact, a slight step can be made by using deep Boltzmann, but the further goal is still unknown. And quantum gravity means that you need many space-times, path integrated. And path integration means that you put some weights for each space-time and make a summation of all of those space-times. And in my case, each space-time corresponds to one neural network with some weight. So it's like you have to make a path integration over weight space. So it may be similar to something like a statistical neural network or graph neural network, but we are not sure. So my goal, the final goal would be to define quantum gravity, and our step is still here. But anyway, I was very happy to find out a way to relate quantum gravity to neural network by realizing this roadmap, and I hope you enjoyed it. Okay, this is the end of my story. Thank you very much.
Right. All right. Thank you, Koji. That was a beautiful talk. Yeah,
Thank you.
Very, very nice work. Thank you for also staying up so late, Japanese time, to tell us about your work.
I hope
It's
my
really
brain worked.
generous of you. So happily, there's a number of questions sort of coming in the chat. Maybe there's order 5 or 6 or something like that. So it's probably best, since people have typed them there, if you could go through those and read off their question for the sake of the video, and then maybe go ahead and answer it as you see fit.
Okay.
And if there are additional questions at the end, we can take them verbally too. Thanks.
Okay. So first I need to look at the chat. Yeah. Is this? Okay, good. So this one, let me read it. How does your neural network approach compare to the Hamiltonian generative network of Toth et al.? So unfortunately, I'm not familiar with this Hamiltonian generative network, but in general, this generative network, so let's see. So in my case, Hamiltonian is encoded directly to the neural network architecture. So I have a strong restriction to the neural network. And because of that, this neural network is interpretable. So of course, you can allow more freedom to the neural network. Then the interpretability or the direct translation to the equation of motion is getting lost little by little. So I hope there is a nice relation to the other approaches using Hamiltonian or finding Lagrangian out of neural network learning, but I'm not sure how they are related to each other. So if the person who asked this question is in the audience, then I hope I answered your question or not. Okay, so let me go to the next question. So here, the question is, did you consider somehow linking your work to the existing paradigm of thinking about the holographic of ADS safety as a quantum error correcting code? I'd like to know if, say, you consider the recent work by Kohler and Cubitt at UCL. So the answer to the first question is yes. And the answer to the second question is no, I haven't. So let me describe the first question more. So the starting point of my work is that, okay, I have a neural network, and then if we say that neural network is interpreted as a tensor network, and the particular kind of tensor network is actually identical to this quantum correcting code by people, so it's called happy code. And that worked very well as a toy model of ADS-CFT correspondence for a fixed background of ADS or ADS-Schwarzschild geometry. So I wanted to generalize that to more general spacetimes, which includes this quantum error correction code. But so far, I'm not successful in that direction, since in my work, I used a very special neural network to represent a spacetime, and it is not directly related to this tensor network of quantum correcting code. So I hope in the future, if I use other scheme of neural network, then I can relate my neural network work to the quantum error correcting codes. All right. So the next question is this from Gary Xu. Gary, thank you for the question. So how is the notion of causality on the gravity side reflected in the neural network? Another question is, if we interpret the depth of the neural network as time, how do we implement the arrow of time through, e.g., entropy considerations? Now, this is a very nice question. For the first question, how is the notion of causality? So in my example of a neural network, the horizontal direction was this emergent ADS radial direction space, and vertical direction, one of the vertical direction is time. So causality is defined with the direction of time. So if I use that direction of time, then I think the neural network can be implemented with this arrow of time along this direction. Since ADS-CFT works with the time evolution, and we know that time evolution equation of the whole higher dimensional space-time can be mapped to neural network, a certain neural network. So if I am allowed to use this neural network, then the causality is in fact encoded there. But so another question about the depth direction neural network as time. So how do we implement the arrow of time? So in my case of this Hamilton equation, the direction of time can be reversed. Since this is a Hamilton equation, so the time direction can be reversed. But if you once include the friction, then this friction actually kills the time reversal symmetry. So once you include this friction force and you discard the Hamilton dynamics, then arrow of time is naturally encoded in neural network. So in neural network, there is a discussion about chaos. Chaos means that the initial condition sensitivity is lost, right? So in that way, I think in every neural network, if it has a chaotic structure and also attractor or something, then this time evolution can be quantified by Lyapunov exponent. And once you have positive Lyapunov exponent, the system is chaotic, so you cannot go backwards. So this kind of interplay between chaotic systems and neural network is, I think, important. And since chaos is also important in quantum gravity to find whether, so it's a good index to find out whether it allows a gravity dual description or not. So I think chaos research in this quantum gravity context related to neural network is also important. That's my comment. Okay, so let me go to the question next here. How can you get a relativistic spacetime, e.g. Lorentz invariance? Yeah, thank you for the question. And I don't have Lorentz invariance. As you see, so once I discretize the spacetime in my way, then Lorentz invariance is lost. This is a very important question, for example, in lattice QCD. So QCD is in a continuous four-dimensional spacetime, which is flat. But if you want to put it on a supercomputer, then you need to discretize the spacetime in a certain way. And once you choose this frame, then it breaks the Lorentz invariance. So what you can do is to perform a simulation on different discretization, and then you check whether they give the same answer or not. So that's the only way you can check whether Lorentz invariance can be recovered, even though you discretize the spacetime. So the answer to this question is that yes, I can start with the relativistic spacetime, but once I discretize the spacetime to make it to mimic, to look similar to the neural network, then I lose the Lorentz invariance. But you can check whether Lorentz invariance can be recovered or not by checking different kind of discretization. And one comment is that I didn't have time to talk about that, but there is so-called neural ODE in which you are free from discretization. So neural ODE actually is about the continuous function weight space, and the discretization is automatic. And in my case of trying to relate quantum gravity to quantum mechanics in lower dimensions, this neural ODE is the best concept since it uses continuous function space as a weight space. So I hope I can come back to this question, Lorentz invariance, in the future by using neural ODE. Okay, so next question. Oh, this is not question. Greg, thank you for your comment. And here is a question. When you optimize the neural network to get the classical spacetime metric, how can we sure it is not the local minimum after the optimization? Yeah, that's right. Yeah, that's right. So this is a good comment about the good question about the regularization. So I didn't tell you anything about the regularization, but when I train my neural network, of course, I introduced regularization. This regularization is to make the weight distribution, I mean the metric function, smooth along this horizontal direction. If I didn't put this regularization, then the resultant trained metric is completely zigzag. If this function h is zigzag along this depth direction, then you never interpret it as a spacetime. Only when this weight distribution is smooth along the neural network, you interpret it as a spacetime. So it is up to your introduction of regularization when you optimize this neural network. And the result, if result is quite smooth function, then you interpret that as a spacetime. Otherwise, it's not a spacetime, but it's giving the correct answer. So there could be many minima in this loss function space. But the the minimum at which the weights are interpreted as a space-time is quite small amount of the whole minimum. So, so for this purpose, I need to introduce a quite specific regularization when I optimize this neural network. And there is a physical interpretation of this regularization. This smoothing effect as a loss function, a regularization loss function, is interpreted as a kind of Einstein-Hilbert action. So what is Einstein-Hilbert action? Einstein-Hilbert action, it gives you a weight of how the Einstein equation is satisfied. If Einstein equation is satisfied, Einstein equation has small number of derivatives, so the solution should be smooth. As I said, the locality notion is related to the number of derivatives. If you allow higher derivatives, then the space-time looks zigzag. So Einstein equation ensures that space-time is smooth. And what is the index of how much this Einstein equation is satisfied for given weights? That is Einstein action. So in my case, this regularization which I introduced intentionally has a physical interpretation as Einstein action. So I hope I answered this question. Okay, so let me, so if you have further more questions, then please, that's okay to go ahead. Right, so let me go to this question. Thank you for your comment. Is there anything on de Sitter tensor network correspondence? Also, what's the exact Swingl's 2010 citation from the roadmap slide? So as for the first question, I think there could be some proposals, but I'm not aware of it. So in de Sitter spacetime, as opposed to the anti-de Sitter spacetime, de Sitter spacetime is for our universe, which is expanding and time dependent. So it's difficult to implement a static neural network on it. So if you allow network itself to expand simultaneously, or if you include some time direction and non-static neural network, then I think there is a possibility to assign a network to de Sitter spacetime too. And also recently in this year of the interesting work about quantum computational complexity and de Sitter spacetime has been proposed very, very recently. So, so in that scenario, we interpret this de Sitter spacetime as a kind of information storage, and then how big the network and how complicated the network is depends on the universe time evolution. And I think that's a very interesting idea to explore in quantum gravity. But so far, I don't know explicit example of relating de Sitter space to tensor network. And what's the exact Swingl's 2010 citation from the roadmap slide? So I'm not sure I understand the question or not, but here, so as I mentioned, Swingl's 2010, so you want to know the number of the papers? I'm sorry that I didn't give you the paper number here, but you can Google it. It's I believe it's the 2010 paper by Swingle. So he proposed the interpretation of this Mera tensor network with the anti-de Sitter spacetime. And that's it. I think that's a tremendous development of relating these two differently looking fields. And based on this, for example, you can compute the quantum mechanical quantity on this side and compare that with the gravity side, like entanglement entropy. So I'm not sure if I answered the question, but let me go on to the next one. Thank you for the questions. Okay, here, I'm aware of this paper, 2-3. This is the answer to 2-3. Okay. So here. Okay, so let me go to the next question. So the question is, in what sense is the metric emergent? So the word emergent is used especially in our field. So emergent phenomena means that in a generic theoretical physics, I think, so starting from some definite concrete degrees of freedom, if a phenomena coming out of these degrees of freedom does not look like the fundamental force in between those degrees of freedom, then you can call this as an emergent phenomena. And in this ADS-CFT correspondence, the quantum gravity is an emergent phenomenon, since in the original quantum mechanics, there is no gravitational force. It's one-dimensional lower. So usually you don't expect something like a black hole or something. But in the end, if you have a nice quantum system and take a large degrees of freedom limit, then if it allows a quantum gravity description, then this whole theoretical description is an emergent phenomenon. And that includes this general space-time, since this quantum gravity is hosted by this general higher dimensional space-time. So this space-time is emergent. And we, in our community, this ADS-CFT, in the context of ADS-CFT correspondence, the space-time in the quantum gravity side is called emergent space-time. And this emergence is very mysterious from the viewpoint of this equivalence. But my point is that if you interpret this neural network states, then here, the emergent part is actually the neural network part. And also, there is a continuation of the question. So let me read it. Also, we talk about space-time emergent from the underlying entanglement structure, entanglement entropy. Yes. Can you represent entanglement in your network? Yeah, that's possible. So there are two ways to answer it. So first of all, let me make a comment on the work by Izan Yo. So he developed the idea of entanglement holographic geometry by starting from a lower dimensional quantum spacetime and use the data of entanglement entropy of this quantum mechanical system to find out the holographic geometry, emergent geometry. So this way actually uses a famous formula called Ryu-Takayanagi formula in quantum gravity in ADS-CFT. And Ryu-Takayanagi formula actually states that once you consider a curved space-time and put a surface like this, and then the area of this surface in this higher dimensional space correspond to the entanglement entropy of the section of this quantum mechanical space. So that's the formula. And if you use this ADS-CFT dictionary, then with using this Ryu-Takayanagi formula, you can probe this general space-time by using entanglement quantities. And Izan Yo actually implemented this in a neural network. So he prepared this kind of looking neural network and then consider the entanglement entropy as a data to determine the structure of this neural network, I mean weight space. And finally, he found that after the training, by using a certain data of quantum mechanical system, the emergent space-time is anti-de Sitter space-like. So I think it's a very nice work. And our space-time is using a different neural network. I mean, different from Izan Yo's one. So I don't have a direct connection to his work. However, the concept is quite similar. So in what kind of data we use for the quantum mechanical data to train the neural networks, that is the difference. So once a given quantum, so suppose you're given quantum field theory, then quantum field theory has a lot of data. It can have entanglement entropy, it can have one point function, which I used for QCD, and it have multi-point functions. So all of these data can be used to train the emergent space. And once you find the consistency among all of these data and emergent geometry, then you say that you find a quantum gravity dual description. Okay, so let me go on to the next question. So this is the comment to the other question. Thank you very much. And this is the paper. Jim, thank you very much for providing the information. And so this question from Takato Mori. Can you tell me which paper you were talking about? So, so my paper, so if this is a question about my paper, then you can just Google it. And then if it's named with deep learning and something, then it's about that. So please, yeah, thank you for the question. If you are saying about some other part of my talk, then please write more comments here. And here it looks the last question. There's a literature linking deep learning and renormalization group. In your model, can you interpret layers of neural network as RG flow? So with many layers, you would go away from the boundary in ADS-CFT, i.e. from UV to IR? Yes. Yes, it's indeed a renormalization group flow. So in ADS-CFT correspondence, it's known that in the this emergent geometry, from left-hand side to go to the right-hand side, as I did in the neural network, is called holographic renormalization. So in terms of quantum mechanics, this left-hand side boundary is the high energy, UV, and right-hand side, the black hole horizon, is the IR. So energy scale, so this neural network is actually the energy scale. So indeed, in any model of ADS-CFT correspondence, this direction of depth direction of the neural network is interpreted as a kind of RG flow. So yes, the answer is yes. And with many layers, I would go away from the boundary. Yeah, that's correct. So from UV to IR, I have a neural network. So input is UV and IR is the output. Oh, so the next question is about the paper. Yeah, I'm sorry. So let me go back to my first slide. So this is the first slide. And Izanyo is my friend in UCSD. He's a condensed matter theorist. And this paper I've written with him, which is a recent one. And before that, in 2017, I think he has the paper on entanglement entropy and ADS-CFT. So please find his paper. His name is Izanyo. And his paper in 2018 or 2017.
All right. Thank you, Koji. It was wonderful to get so many questions. One of the fun things about this direction the last month has been that there are so many questions. You just got a full half hour of questions. That's great. So thank you for the beautiful talk. I'm sure some of you probably have some more questions for Koji. Feel free to contact him on your own, and I'm sure he'd be happy to answer them. We will be announcing our next set of 5 speakers soon. Some of them are already on the website, but the next Physics Meets ML seminar will be 2 weeks from today. So let's thank Koji one more time. You can
Thank you
hear
very
me,
much.
so I will clap. And it was really a beautiful talk. And again, thank you for staying up so late Japanese time. I mean,
Thank you very
really
much.
us, so thank you. So, all right, thanks everyone. See you in 2 weeks.